Hello, everybody. Welcome to Forging Ahead, a deep dive on the U.S. Department of Energy's FORGE initiative, which stands for the Frontier Observatory for Research in Geothermal Energy. The FORGE project is DOE's, certainly the DOE Geothermal Technologies Program's flagship initiative, and within larger sections within DOE, this is also a very major program, and it's been a long time in coming, and there's been great results to date, and we're going to hear about some of those. My background is I've spent the better part of my career in geothermal research. I'm not a practitioner, but a researcher, and primarily around drilling technologies and such. I've had a long association with the FORGE project, first as you'll hear, it was a competitive down select process. I was one of the competitors, and my team did not move forward, but I've had the good fortune of now being on detail to the Department of Energy as an advisor and helping both the Department of Energy and a role within the current FORGE project as the lead of the Science and Technology Analysis team, which provides support to the management of the FORGE project and its execution. We'll start off with introductions, and I'll ask each of you to introduce yourself, speak a little bit about your relationship to the FORGE project, and we'll get started after that. John, why don't you kick it off?
Hello, my name is John Mclennan. I'm a faculty member in the Department of Chemical Engineering at the University of Utah, and I'm one of the co-PIs of the Department of Energy's FORGE project. Now, unlike my colleagues, my background is primarily in hydraulic fracturing, including some stimulation at Fenton Hill several decades ago. But I do have patient colleagues who are doing their best to teach me about drilling, and I was involved in managing the first inclined well drilled on the FORGE site.
Thank you, John. Fred.
I spent most of my career in operations drilling as an operations engineer. I retired about 10 years ago from ExxonMobil as the chief engineer. After which I became a professor of practice as teaching at A&M. I'm currently involved with a DOE-funded project with Dr. Sam Nonyert here at A&M to develop a workflow for the geothermal industry, similar to the limiter redesign approach to performance that has done pretty well in petroleum. So a good part of our project is workflow. Another part is taking all the technologies that we have developed under that umbrella, limiter redesign, physics-based limiter redesign approach to drilling, and applying them to the degree possible in a geothermal operation. So we were involved in the well with John earlier, and now we're involved in the current well, Sam and I, with training and daily support and implementation of those practices. And well, I guess we probably have 2 or 3 weeks left of the project on the well, after which we'll be collecting learnings and publishing those early next year.
Thank you. Junichi.
Okay, thank you, Doug. My name is Junichi Sugiura. I'm very honored to be here, and I'm based in the United Kingdom. I'm the Vice President of Symbian Technologies, which is a technology startup company founded in 2015. And we have developed high-frequency drilling dynamics recorders, digital rotary steerable systems, intelligent wired motor, and among other things. So Symbian Technologies and the sister companies, Scout Downhole, Scout Drilling, and Canamera Coring, are all under Turbo Drill Industries, which is the parent company, and provided drilling services and equipment for the FORGE project, which is 16A, 78, 32, which is the previous well, injection well, including high-frequency drilling dynamics recorders, mechanical particle drilling tools, instrumented steerable motors, friction reduction tools, coring tools, and so on. So our company develops new technologies and tools for oil and gas industry, but we also have involved in geothermal, both cutting edge EGS and close to geothermal well drilling. I'm very pleased to join this panel discussion. Thank you.
Thank you. Tom, why don't you go ahead?
Yep, thanks, Doug. Yeah, my name's Tom Roberts. I'm a mechanical engineer. I started with Reed Hyclog, now part of NOV, in the UK some 30 years ago. They're a manufacturer of premium drill bits for oil and gas. So I started there as production engineering, design engineering, and then in 2001, I transferred to Houston, focused on drilling improvements, later managing research and development in that area. And today I lead a highly focused team basically focusing on improved PDC cutters, diamond cutters for drilling through hard rock. So we have a team that's focused on the cutter grades and teams that are focused on the efficiency of shapes that can be applied to diamond grades to drill more effectively. And we have a lot of equipment to prove that out and test that, which hopefully we can talk about today. My role with Utah Forge really is to advise on the type of drill bits and more specifically the PDC cutters that are being utilized. We focus on making sure that these cutters are designed specifically for the application to withstand you know, any thermal abrasion or toughness improvements that are required. I'm relatively new to geothermal, but I would say we're learning extremely fast and excited to share, you know, 30 years of oil and gas expertise and apply that to geothermal markets. So it's great to be here. Thanks, Doug.
You bet. That's it's been one of the goals of Forge is to bring in technologies from parallel industries and apply those here. And it's certainly been a passion on my part for a long time. So I'm looking very much forward to this conversation. I do think that we should start off this discussion. I assume that everybody knows what Forge is because it's been such a big part of, you know, a number of our lives for a long time, but I suspect they don't. So John, I'm going to throw this to you, and it'd be nice if you would, you know, provide a background on Forge, what you see the goals of Forge are, how was the Utah site chosen, and basically what are the plans moving forward from the beginning to the end?
Sure. So as Doug mentioned, Forge stands for Frontier Observatory for Research in Geothermal Energy. And let's just parse that a little bit. It is in fact a field laboratory, and it's designed to provide an R&D platform for developing technologies that will make EGS commercially viable and geographically attractive. And the choosing of the Forge site took a number of years. The Utah Forge site was down selected from 5 initial promising locations in the Western United States. 2 sites of these were high graded, and one of those, as Doug mentioned, was the Fallon, Nevada site that was proposed by Sandia National Laboratory. And the second was the Milford, Utah site proposed by the University of Utah. Now, ultimately, University of Utah site was selected. Nevertheless, all 5 locations had favorable attributes, and some of the attributes in the selection criteria, we can go through those. The first one was that the temperature needed to exceed 350 degrees Fahrenheit at depths greater than 5,000 feet. So the intent here was an adequately hot reservoir and challenging enough drilling conditions to get to at least 5,000 feet. Now, currently at the Forge site, as of today, we're drilling a well that's now at 8,500 feet, and the static bottom hole temperature is in excess of 350 degrees, or circulating bottom hole temperature has been in excess of 350 degrees. We anticipate static bottom hole temperature approaching 450 Fahrenheit. The second thing that an EGS reservoir requires is low permeability rocks. And at the Forge site, these rocks are granitic, various shades of granitic, and people sometimes call them granitoids. The third thing, and maybe one of the most important things, is induced seismicity. And as we know, the Achilles heel of some enhanced geothermal programs has been the occurrence or the potential for induced seismicity. Now, it turns out that the Milford, Utah site has been monitored extensively by the University of Utah seismograph stations since the 1980s, and it has shown acceptably benign seismic characteristics. The fourth thing that we have to worry about are low environmental risk. There are no endangered species, the groundwater is not potable, and there is no competition for surface land usage. The final thing, and this is an important one, is that it needs to be a conductive heat transfer regime rather than a hydrothermally convective heat transfer regime. And that indeed is the case at Forge. So what are the plans start to finish? Well, I'll try and do that in 30 seconds. And the plan in less than 30 seconds is as follows. Surface mapping and seismic evaluations were initially done. Subsequent to that, reservoir characterization involving logging, injection testing, small-scale stimulation evaluations, and other in situ tests were carried out in vertical wells. The third aspect, and it's ongoing, is drilling vertical wells for monitoring equipment. And this monitoring equipment includes high temperature geophones and fiber optics cables. So there are 5 wells that will be used in the monitoring process. The fourth and most important part of the plan, or one of the most important parts of the plan, is community engagement and outreach. That's always necessary early on in these programs. It's absolutely essential. Then we get down to the part that we'll talk about here today primarily, is that's the drilling of 2 extended reach wells. And you'll hear quite a bit about the first well. Junichi has already mentioned it. That well is coined as 16A 7832, and it was completed in January 2021. It landed at a target of 65 degrees tangent, and that tangent was maintained for about 4,350 feet to a total true vertical depth of 8,550 feet and a measured depth of 10,987 feet. Bottom hole temperature on the order of 435 degrees Fahrenheit static. Next, and this will happen sometime later this year or early next year, there will be a 3-stage stimulation at the toe of the inclined well. And that will be subsequently followed by another well to penetrate the triangulated microseismic cloud and create fracture intersections as part of a heat exchange system. And all of this is along with ongoing DOE-funded research that will use this laboratory to evaluate isolation technologies, in situ stress, fracturing protocols, and geoscientific issues. And so one question we've been asked sometimes is, well, what outcome will be considered a success? And as you'll hear from my colleagues on this panel, there's been outstanding success already in terms of adapting and refining drilling technologies. And this may not have been part of our initial expectations on the Forge project, but this has been a very, very favorable outcome up to this point in the project. And Doug, maybe I'll leave it at that for the time being so we can get on to some of the drilling aspects.
Great, thank you, John. There's been five wells drilled to date. Is that correct, John?
5 verticals and 6 in total.
So 6 total, 5 deep. And so what I know is the initial exploration well drilled at, I would say, normal geothermal rates. I don't know I can't remember the exact numbers, but averaging 15, 20 feet an hour, something in that order, I believe. Is that correct, John?
Yes.
Yeah, so that was the initial exploration well drilled several years ago. And then they've moved on and drilled a number of other wells, with the 16A well being the next deep, challenging well to drill. And they drilled significantly better than the 15 to 20 feet an hour. I'll let people talk about that. And they're currently drilling another monitoring well, a deep monitoring well that is drilling at even higher speeds. So the question I'm going to ask is how'd you drill so fast in 16A? Who wants to take that? Brett, you want to start?
Yeah, I'll volunteer for that one. It sounds like good news, right? So In some sense, the answer is that, first of all, we use BDC bits, which are inherently more aggressive. They indent more for a given weight on bit. When you rotate, you destroy more rock per minute. So that is just intrinsic. And the question has always been, well, can they survive the rock though? But let's set that aside. I think Tom's probably going to talk a little bit about that aspect of it. But the way you actually drill faster then is you increase the weight on bit. And it's really simple. The way a bit works is that you apply weight on bit and the cutting structure indents. Now, a more aggressive bit for a given amount of bit indents more. That's the difference. But weight on bit indents, and then as you rotate, you destroy all the rock to the right of that indentation depth. So drilling faster is as simple as raising your weight on bit. The bit will indent more, you destroy more rock per minute, or turn the bit faster and you get exactly the same effect. If the bit is efficient, that's a linear response. I get a really predictable. If I get 2 data points, I can tell you what 3 and 4 are going to be, how fast we'll be going at another weight on bit. So in general, many people don't realize that it's that simple, because what happens is that as they raise weight on bit, some dysfunction occurs. It's not normal, it shouldn't be there. So what happened in the petroleum industry was we learned how to use mechanical specific energy, watch the energy consumption per bit, MSE. And what we learned from watching that was when we could see when the bit wasn't efficient. And then we learned a lot of things didn't work the way we thought. And that's began in around 2004. Over the next some years, actually, primarily at ExxonMobil, that challenged the idea of how bits work a little bit. When we started really focusing on what are these dysfunctions, what are their physics. If I have stick slip, for example, I'm raising my weight on bit and the bit's becoming dysfunctional, not drilling faster like it's supposed to, and I know how to identify stick slip, then I've got about 4 responses the driller can see, do, and decide, and I've got 10 engineering redesign options I can consider to address that. Well, so the enlightenment, being able to see the energy consumption of the bit and know what it meant was a big deal. And it really opened up doors for performance. And that's what we're trying to do in this project here. And it's about knowledge. It's not about technology so much. I don't think we've used any brand new tools. There's a little bit of bit evolution occurring on these wells, which has been really good. But I would say most of what's happening in ROP is that it's knowledge-based. So in this process of implementing a physics-based, meaning understand the physics of things, and a limiter redesign, physics-based limiter redesign workflow, you say, we're going to teach you all these physics, the driller, the DD, and then we're going to approach the well by saying, raise weight on bit until something limits you. And whatever that is, figure out its physics, figure out what the driller can see, do, decide, figure out what the engineer can redesign, and redesign that to extend the limiter until something else limits you, and whatever that is. And most of the time, it's not the bit, actually. You start doing these weight on bit step tests, you do this methodical approach to performance, then you run out of motor differential. Well, go get a different motor. Or the motor has enough torque, but you think you can go more speed, that's a different motor too. Or whatever limits you, it's interfacial severity, I have to do this, bit balling, I have to do that. For all of these different kinds of limiters now, the petroleum industry has maybe a decade and a half of experience of just building those packages of what can you see, do, decide, how do the physics really work, and what can you re-engineer. And then the key then is for the organization to just be relentless about continuing to pursue that. Now, what's funny is that we don't do that. These teams have, the team that John was involved in, the current team out there, and the whole Forge culture, the opportunity, the setup is there to prove new stuff, right? So it's been a fabulous opportunity, and they are doing and doing and doing, and that's why they're drilling faster. doing step tests, they're identifying limiters, and whatever they are, they're managing them. At the same time, they're watching energy, they're watching vibrations. We've had some of Zunichi's tools in the hole, some real-time tools telling us vibrations from Scout. Well, all of that doesn't help you unless you have an actual workflow that says that you redesign and you change, and keep going, which is what they're doing. It's just, so in the end, I would say we're drilling fast because we raised weight on bit. But the real question is, why haven't we raised weight on bit before? Because we're not using a lot of actual new technology. And the answer is that there's knowledge at the rig site that didn't used to be there before about how to see what's happening when you raise weight on bit, how to stop when you should stop, how to redesign what's limiting you, and how to keep going. So this is more of a, maybe it seems semantic, but how you manage knowledge, how you create it in a drill team and sustain it, which is really hard in discontinuous programs. How you create knowledge and sustain it is a different thing than technology. Everybody has the best technology. You just call up NOV or you call up Sandian and you got it. And it moves. If you go get it, it's sitting there ready to go. If you have well planning time, you have some business model issues in geothermals. It makes that hard sometimes, but technology is moved extremely efficiently by the vendors and the service companies and the drilling contractors. Knowledge is extremely difficult to move because whose job is it to train the whole rig crew, the DD, everybody, and all these different kinds of things that aren't generally actually known. The way people drill and have my whole career is you go try different weights on bits and you try to find the sweet spot. Well, it turns out there's no such thing as a sweet spot. There's a place that's not as bad as every other place. And that's what's been happening. If I understand physically this whole, what's happening, physically, the physics of it would say, then I stop seeing anything as a sweet spot and I say, I'm being limited to a spot, and now how do I redesign what's limiting me from just continuing to go up? So knowledge management is a really different thing than technical management. And so we locked in, we did about 60 feet an hour in the 8 3/4 hole in the granite on the 16A and felt really good about that. We're drilling a 10 5/8 hole now on the 78B and locked in at 100 feet per hour. And that is what happens when you physically understand the limiters to what the bit can do when you apply weight to it. And you continue to redesign until you get to more weight. We're at 65,000 pounds weight on bit. And I would bet that the wells that were drilled around us originally probably ran about 25 to 35, and we're worried that was too much. So I think weight on bit, but mostly more so, what limited you from us all from applying weight on bit? And it was mostly knowledge. And that's what's been, a lot of what has happened has been brought to the table.
Thank you. Thanks. So Tom, real quick, doesn't more weight on bit wear the bit out faster?
Well, that's a good lead in. Yeah, definitely weight and bit is key, as Fred's mentioned, but we developed cutters, many years ago. They would be, the holy grail of the best cutter for all applications. But actually what we found is that we can develop cutters that are specific to various applications. And in this case, we need a cutter that's going to be thermal abrasion resistant, but also have toughness and we're looking at the weight and bit per cutter. That's important on this design. One of the things that, and there's a handout that we've provided next to for this session to look at. But what we looked at here is we've done a couple of things. One is we've looked at thermal resistance on cutters, and we tried drilling on Sierra white granite, which is very similar to the rocks that we're drilling here in Forge. And we found at a very high surface speed and very low depth of cut, even if it was a thermally leached, performance cutter, it would wear out very quickly. And so if you spin it fast, very low depth of cut, then the cutter would wear out. And we then took another grade of cutter, and took a large depth of cut. And when I say large, we were reaching 7 millimeters depth of cut as opposed to 1, and reduced the RPM threefold. We were able to not wear out the cutter. We were amazed that we could in fact, we ran out of rock on the test. And I've shared these results with Fred. I think he was surprised to see that, but we've known this for a while, that drilling with large depth of cut is the key with PDC drill bits for efficiency. So furthermore, I think the issue with going with low depth of cut and being conservative, I'll use that word, when we try and find it, as Fred put it, the sweet spot, is that eventually a wear scar is going to form. And once that wear scar forms on the diamond layer, you get a larger surface area. That means what you do to drill faster, you pile more weight on. So we're almost doing things in reverse. We're piling the weight on, we're creating larger wear scars, which creates more friction, more thermal abrasion damage, and eventually the drill bit will fail before its time. So PDCs have come on tremendously over the last couple of decades, go into higher pressure platforms, and they're able to take much higher weights, and they're designed stronger to fail the rock. So if we can go with a larger depth of cut, we reduce that sliding distance. This is the key to it. If we were to reduce the sliding distance by 50%, then we're able to reduce that wear scar generation. So the cutter stays sharper longer and is able to penetrate the rock. So that's the key to it. One thing that we did see, though, is that the penetration rate started fast on most of the bits that we've applied. Weight was key to getting fast ROP, but we did see a drop off. So that's something that needs some more work on in that area. And one area that we're focused to overcome that is to shape the diamond PDC to better fail the rock. And we did some interesting tests in the lab. One was with a Sierra white granite, again, as we said earlier, 28,000 kpsi rock. And we also drilled on the hardest we could get. In fact, they used an explosive to get it out. It's a quartzite of 56,000 kpsi. And what we found is we kitted one of the drill bits out, and these were sort of 8 3/8 bits, drilling onto the rock atmospherically with full round cutters. And then we took it up in 10,000, 20 to 30,000 pounds weight. We then did exactly the same drill bits with a V-shaped pointed cutter to point load the rock, indent the rock, and we then took that up in 10, 20, 30. What we found is that the round cutters would spool faster than the sharper cutters. The sharper cutters were able to indent and fail the rock before they failed. In fact, we got to 20,000 pounds on repeat tests and repeatedly failed full round PDC cutters that way. So this is why we were convinced that for hard rock challenges, we were able to try the V-shaped cutter, which basically went to 20, and then we took it up to 30,000 and still didn't fail. We did see some minor hairline cracks, which means that in the quartzite, it was getting close to its structural limit. And this is what Fred's been proving out with his team and the rest of the Forge team, is to understand what is your limiter and how far can you take it. So I think the weights, Fred, were in the 10 5/8 section. I heard that reaching even 75,000 pounds. This is beyond the normal range that you would reference for that drill bit design. And I think the average was more like 65,000 pounds. But by doing that, they've reduced that sliding distance, which has reduced the wear scar generation, and able to more effectively penetrate and drill the rock with lower MSC. So that's part of the key to making it work. And there's more refinement needed. The question is, how far can you go? And then I think one of the things that's been in our favor for the Utah Forge work is that the basement rock is hard, but it's not interbedded so much, right? So one of the issues that we have in oil and gas is we're drilling through soft sedimentary rocks, shales, sandstones, you name it. We're still dealing with abrasion and thermal failure. But then we hit this hard stringer, and that's when it becomes a bigger challenge, because if you're piling that weight on at that point, that's when you could get a breakage of the cutter. So what's working for us at Utah Forge at the moment in this basement rock is that it's hard. You drill with high weight and bit, and that's what's working really well, because we have the cutter technology, we have the right bit designs.
Well, thank you.
Yeah.
So Junichi, this is a little off script, but you were involved in the 16B well and the technology you applied. Can you speak to the motors and some of the advances that were employed there?
Yes. So this is in general. We had a shale revolution 15 years ago, or maybe started 20 years ago, and during the last decade, we drastically improved the drilling equipment's capability. So of course, bits is involved. Bits are tougher, much tougher now, and in order to support very high torque at the bit, the motor has to evolve. So more torque, more power. Then motor itself can support this torque demand. That started fading transmissions or stators, the bend angles around the bend, some other areas, torsional fatigues. So everything as a system actually evolved in the past 10, 15 years. So in this case, in the previous well, we started with a lower RPG, revolutions per minute. RPG revolutions per gallon motor, and then we switched to a higher RPG motor that really matching the bit and the motor, that improved the rate of penetration. So vertical, we had an average on bottom ROP rate of penetration was around 10 to 20 feet per hour. And then the carb section, of course, this is sliding involved. So it'll be a little bit slower, you assume, but actually we went from 10 to 20 to 30, 40. And finally, tangent section, we had long 65-degree tangent section for 5,000 feet. This is also when bits, between bit and all the drilling system is being matched and then optimize the performance. So finally, we went to around 50, 60 feet per hour. This was the highest ROP we marked. And of course, Fred said, in the latest well, they even got the higher ROP. But this is because of the experience we had with the previous well we finished in January of this year. So besides, we had a motor, some other, drilling equipment. Drill bit itself, we tried the 30-millimeter cutters, but we also later tried the 16-millimeter cutters, which works better. And later we also found that in a lateral section, removing depth of cut feature from the drill bit actually improved the rate of penetration. So there are a lot of small incremental changes we made, and finally we went from 10 to 20 feet per hour to finally 50, 60 feet per hour. And then of course Fred and other team carried on this knowledge and experience to the latest well. So I'm not involved in the latest well, so I myself is very, very interested in hearing how they did it. And they actually the secret sauce that Fred mentioned is the workflow and the knowledge and actually the discipline at the rig. So that's really interesting secret sauce for the success.
Thank you. So again, a couple things here is so you drilled fast in 16B. I think you've talked a bit about how you've gotten faster in 78B. If you want 16A, and faster in the 78B well, if you want to comment on that, that's fine. But my real question is, what kind of challenges did the team have to overcome to see these kinds of improvements in drilling rates? Were there any particular challenges that people want to note? I'll open up to anybody.
I'll take that one, Doug. From the drill bit perspective, I know that typically we have offsets, right? When we're drilling, we refine and we improve the cutter technology, we improve the bit designs in any application. That's one of the things about the industry, is that we never stop still. We're always improving, and just as Fred mentioned, overcoming any performance limiter from the design perspective. But the team here didn't really have any offsets to go by. And, when we started the 16A well, it was a case of, well, what do we use to drill hard granite, right? So all we had was rock strength analysis and estimations. So the guys looked globally at our experience in areas such as Oman or New Zealand and other sort of geothermal markets, Poland as well. And the approach was that, yeah, this is a team. What we'll do is we'll choose bits that are related to hard rock drilling, but let's have a range of them available so that we can quickly move to those different designs. So we had designs that were 5, 6, 7, even 8 bladed designs available, as we're drilling now with the 10 and 5/8, as well as 16 and 13 mil cutters designs all ready to go, so that as we learn from each application in the morning meetings and the team events that happen, we're able to basically move fast and try something different. And that was the beauty of that first well, the 16A, was that we tried so many different things, and that allowed us to learn and take it to the next step. So I would say that was the main challenge, was not having the offsets. But now that we've started and learned fast, I think we can just build from that.
The process side of that, the kind of the approach to performance, the methodology that has been built around physics-based limiter redesign, and what we've done at A&M is we'll go to a company and research their digital data, their history of their wells. We'll identify their limiters for them in advance. We can do that now. And if they choose a programmatic initiative, if they say, I'm going to be so bold as to move from this empirical world where we just try stuff, kind of, and learn from it, okay, to this world where I understand the physics of everything, then with those companies, and this includes quite a few of the major independents in the US, we've done 2 full days of training for the entire rig crew. That's the driller. That's any of the crew that they want involved. That's the mud engineer, that's the directional driller. 2 full days of what are the physics of important stuff. Now, in our curricula, we built a class at A&M that we teach 134 different practices. And for everyone, it's a physics. What's the physics? What can the driller see to decide? What can engineer redesign to extend that limitation? And everything is seen as a limiter, not trouble or whatever. It's very aspirational. Well, those 2 days include about half of all that full semester of work, and you've got your people who do the work are in that class, and their bosses, bosses, hopefully. So you have now an organization that's kind of got fertile ground with all this knowledge. So, for example, the really profound thing Tom said: higher weight on bit makes the bit last longer. And he mentioned sliding distance. You indent more. You imagine one cutter spiraling into the earth. The deeper depth it's traveling at, the less slide it has to get somewhere. So you double weight on bit, you might double the life. And who believes that? Nobody. Nobody believes that. We were all taught, oh, okay, but we're optimized. If we raise the weight on bit, we might wear the bit out faster. We ran around believing that for half a century. And well, for 10 to 15 years now, teams that have been taught that's not true. Now what happens? Well, now they say in their head, they said, okay, now I'm willing to do it. Management, we should try that. I'm willing now because I physically understand that cutters wear from sliding at the tip, and higher indentation depth means less sliding. I have a physical model in my head that now makes it acceptable for me to go out and try something. And I'm not going out and saying, okay, we'll drill 5 wells with higher weight on bit and see what happens. We're watching every foot by foot, watching MSC, watching our data, doing step tests every few hundred feet, doing another step test, make sure nothing dysfunction's going on. We're managing all of that. And because we have knowledge, because we know how to do that. Tom, we got our weight on bit up to 65,000. Tom told us we could do that, but you could have done that before. And so could any other industry. 65,000 is now a really common number in West Texas. And you go back 5, 6 years, and I would say everybody was at 45. Same knowledge, right? And what it's done to that industry is the same thing that's happening in these wells here. It's the crew knowing it's okay, that it doesn't make it happen, but it enables it to happen, and it creates a crew that's willing to change how they work. And it moves you from thinking that you have to drill a bunch of wells. You have a success with that. So I didn't say this, but we started, I think, Tom, we got runs at about 400 feet in the granite on 16A, and we thought that was great. And we kept, with the weight on bit, sliding distance, you made changes in where the work rate was on the face of the bed. We got up to 700 feet and thought that was great. We just had a 2,000 foot run in this well with 65,000 pounds on it. Again, proving the physics. Well, now the team has seen the physics. You know, you told me that story and I didn't believe you, but you know what? It made sense to me, and well, now I've seen it. And so there's a progression happening that happens in every team, and it's progression that the geothermal industry as a whole, you know, needs. But you ask what challenge is. The challenge from a knowledge management standpoint is what we're proving and have proven at Forge works the same in West Texas, and it's going to work the same in any other geothermal well. World is world, stick slip to stick slip, depth of cut, higher reduced sliding distance, makes the bit last longer. Except for the interfacial severity thing, which we'd have to talk about. So, but how do I get a team, their head, in a position where they're willing to go do those things? And you know, Doug, you and I have been involved in a well before, and I know you appreciate the challenge with that. You have to teach them the physics, and that opens the door.
Right.
If you say, I've done it and it will work, we did it at Forge and it'll work for you, why would I think that's true? I'm somewhere else. You say, here's the physics of how it works. Does it make sense? Well, I'm not sure. Well, let's go to a step test and let's see, and we'll prove it on your well. But now you know what we're trying to prove. And once we do it once and prove it once, you know it's true forever, right? And that's how you revolutionize an industry. We're going to have to figure out how to get knowledge into more teams and more teams and more teams. It's a little different than what they have.
You know, Doug, there are a few challenges left, mind you. And one of them I'd like Fred to talk about, and that's particularly the amount of reaming that we had to do on these wells. You know, we want a relatively smooth wellbore so we can get a good cement job and avoid casing integrity problems and to run cable. But, you know, one of the things that I think Fred can talk about is the amount of reaming that we had to do in the spiraling that existed in some of this hole.
Well, you know, 10 to 15 years ago, we started getting computer-generated 3D images of our boreholes. That you can get that from your FMI log, fracture identification log, if you process it right. And you literally look at three-dimensionally, what does your borehole look like? And you start to see that we've cut a lot of features in our borehole. Our formations, you know, your formations generally in geothermal are extremely stable, highly what I call machinable, and they don't break and collapse very much at all. So if you cut an 8.5 inch hole, you got an 8.5 inch hole. And it stays that way forever. The problem is the hole does this. And then you try to run a tool through it that needs it to be concentric, and it's hitting ledges and offsets. So there's the ultimate, well, and there are things that we can do that help us wiggle and waggle our way through that. But those take time, and sometimes we have to cut those things off, you know, and that's what we had to do on 16A. To drill directional wells in granite, you're going to get a lot more of this kinky thing going on with bent motors. So the low-hanging fruit is a rotary steerable. It rotates the whole body and drills a smoother hole that is durable enough. And different practices with bent motors so that we don't kink things as much. So the bent motor opportunity is largely in reducing the bend. The bend you have in there, you're rotating a bend and you stop oriented to drill in one direction. That bent motor creates a mass imbalance. And so it makes you whirl whenever you rotate your string, and beats the bit up on the end, but it also makes the bit cut sideways and creates some of these features. You slide and rotate, you have features, different things are going on to create these features. And granite is so unforgiving that features like that would wear off as you drill ahead in some shell and most places, but here they don't wear off. They're going to create tremendous sliding friction, and you can't transfer your weight to your bit, so you drill slower. Now your bit doesn't have weight, so it whirls more, and everything cascades on you. So one of the things is lower bend. So what we experiment on the current well drilling the vertically is, rather than run the traditional 1.5 motor, we're down to a 1.15. A lower bend. I mean, it's just simple things like that. When you have the knowledge and you've been to training and you've seen these pictures, you're suddenly thinking, oh, now I understand why I have drag. People are telling your whole career, the well or swells, it swells in and grabs you. No such thing. Virtually anywhere in the world do you have that happen. Now that we've adopted, developed, and built all these practices to make tight hole go away, we don't have tight hole, in most places. Granite's just a lot less forgiving, so we have to be smoother and smoother. Longer gauge PDCs, lower bend motors, better management of whirl, and BHA design, it fundamentally doesn't flex and whirl as much whenever we rotate it. And that's in its infancy with bent motors. With rotary steerables, we can design rotary steerables that run really quiet, but a BHA that's pushing that bit back and forth is cutting the side of the hole with the bit. And we've got to get that a lot quieter. No one's wrong, no one's bad, no service company's bad or whatever, and it's the wrong approach. What we say is, what limits you from making it quieter? Now what limits you from making it quieter? And you do something, and you say, now what limits us? And you chase the limiter redesign concept, and you'll get there. And when we started focusing on what we call borehole misbehavior at ExxonMobil, and of course we're running 17 drill teams worldwide, 16 of them are having to ream. 1 year later, only one was reaming.
So the workflow is basically is applicable to anything from drilling to the general work to accounting. It seems it's really an approach to addressing problems as opposed to a recipe.
If I know how something works, then I know how to fix it.
Right.
And that's pretty obvious, right? But it's also stop focusing on trouble time so much, because the things that limit your performance are actually not broken. If you're automotive differential, you don't say I have a broken motor. You don't run Zanucci Scout Crew off, you go get another motor. And that's what most performance limiters are, very normal things. They're just normal parts, but we don't see them as a challenge to be overcome or changed. Instead, we're all taught now, particularly today, there are college students and all that with big data and all that, we're taught to optimize. Optimize means that you recognize all your limitations, these risks, and you live within them. And you do a bunch of fancy math and you say, look how smart I am. I'm not getting in trouble. I'm optimized, right? And that's, to me, that's what optimization means. And time after time, what you see is someone will say, well, no, when you optimize, of course you're going to redesign. No, you don't. You really don't. We had an offshore platform with a 12-inch auger carrying cuttings. The drill rate was limited to 100 feet per hour for 20 years because the auger would pack off if we drilled faster, carrying our cuttings away for 20 years. And then we found out there was one place where it necked down to 9 inches to go through a bulkhead, and that's where it was packing off. We'll cut the bulkhead out, put a 12-inch all the way through, did that, and the next well, they're drilling 300 feet per hour, drilling 100 feet per hour for 20 years. Make one change because they had the limiter redesign philosophy. They didn't say what's broken, it wasn't broken. They said, what limits me? And that's how profoundly different that is. In our own lives, the example I always use is, if you ask me what's wrong with marriage, I'd say, well, not a lot, but if you ask me what limits it from being better, if I don't have an answer, my wife does. And here's this, probably a pretty long list, right? It's a very profoundly different approach to performance to just say what limits me.
Yeah.
from
Hey.
whatever metric, what limits me from getting more heat out of the ground without losing it? What limits me from, and like you say, it's very applicable. It's played out really well in subsurface engineering and frac design. And it's within ExxonMobil, you know, I taught master's classes to other functions in it. And interesting enough, the people who were most excited about it were our contract negotiators, because they had really never thought about what limits me from achieving what they were trying to achieve. In the part where you're required to go figure out the physics of it. And for them, it meant go sit down and talk, you know, go sit and talk to the National Oil Company and ask them, well, what is it you really want out of us? And they never really did a great job at that. So like you say, Doug, I think it's just philosophy-wise, it's different, and it's broadly applicable. You know, what keeps me from being a better person.
Thank you. We're getting a flurry of questions coming in, and I know we haven't gotten through all of our pre-discussed questions, but there are questions relative to plans. Can you describe more about, plans for, well completion, your stimulation plans, challenges you see and challenges that you have seen, and where the potential touch points are in terms of technology development and evaluation of what you have now. John, maybe you want to hit on that, and Junichi, maybe you want to comment.
I can kick off there. The plans for this fall are to pump 3 stages at the toe of the first inclined well that was drilled. And subsequent to that, we'll drill another well to intersect the microseismic cloud from those 3 fracs. And with the first stage will be slick water in a barefoot section of the well, walking the rate up to 50 barrels per minute. And then after that, we'll shut it in. We'll let it shut in. We'll move up hole and we'll perforate and frac just above the shoe of the 7-inch casing. We'll repeat the slick water treatment. There'll only be 1 cluster, 10 feet long. Perforations haven't been formally decided, depends on the vendor. And we'll walk the rate up as much as we can get it, but we think it'll be somewhere much less than that, 25 barrels per minute to 35 barrels per minute. Then we'll go up 1 more section, and we will vary 1 more thing, and we'll go for viscosity. At some point in the future, we may have to pump sand in these holes, or not sand, man-made proppant in these holes, particularly to hold open the entrance to the production well. We're looking for frac hits. We're not avoiding them. We're looking for frac hits. And the entrance to the production well is what needs to be propped. And so we'll pump a viscous fluid. We have a couple of candidates in mind. And once again, that rate will probably be about 25 barrels a minute. But huge challenges. Isolation remains one of the great challenges. We've had poor luck with bridge plugs and packers in work that we've tried at Forge, more so with packers than with bridge plugs, and we'll be more careful in terms of our tubing loading evaluations, I think, in the future, if we use packers. We will be pumping down 7-inch if at all possible in the upcoming stimulation. The second is the fluids. We think we have viscosified fluids that will work, but that's yet to be seen. The third challenge is perforating. I mean, there are explosives that can deal with the temperature. We really don't know what the charges are going to do. I mean, I was talking to a couple of folks from Owen yesterday, and they figured that in granite, you might see 3 to 9 inches penetration. And we want to intersect natural fractures, or at least we think we want to intersect natural fractures. And that remains one of the great debates in terms of treatment in these crystalline formations. As we've seen from a number of recent experiments in the Permian and the Eagle Ford, it seems like we get relatively planar fractures in some of the shalier formations, whereas in these igneous formations, there's a lot of natural fractures, and the fracture toughness and the integrity of the matrix is high. And so the anticipation is that natural fractures will play some role. We don't know how much in terms of controlling, and that is one of the things that we want to find out. And we also think that the viscous fluid may preclude some entry into the natural fractures. And the fourth and final thing that we're always worried about these fractures is short circuiting. We do not want interference between subsequent stages because we want to maximize the amount of surface area that's occurring. So treatment is really going to be quite interesting on these wells, and we'll know more later.
Yeah, thank you. So in terms of, some questions have come in about, further completions. Do you want to comment on the role of R&D in these wells, John, quickly, and how different stimulation technologies may be tried based on people's awards for research?
Sure. So one of the hallmarks of the Forge program is that it's not just a Forge team drilling wells and doing some fracs. There's a substantial amount of Department of Energy money that's been allocated to solicitation-based research. And up to the present time, there have been 17 awards made. I think 10 or so, the contracting has been completed or close to being completed. The others, it's moving ahead. And these will look at different kinds of isolation technologies, including technologies where you can control the flow into a completion at some time in the future by mechanical methods. Techniques where you're looking at different packers, including metal to metal packers, sliding sleeves as a method for isolation as opposed to frac plugs. A lot of geoscientific evaluations to look at in situ stresses and really understand this whole problem about natural fractures. So there's been one round of solicitations. There have been some fantastic proposals that have been submitted, some fantastic proposals for instrumentation and running fiber optics. And it's really going to make a big difference in terms of understanding the stimulation technologies in the future. So basically our job is just to create the laboratory. The real R&D and the real learning is going to come in the next couple of years, where people are actually trying out different technologies per these solicitations.
Thank you. Junichi, we have a broad question came in about, and in fact, maybe John, you'll want to jump in on this, but the biggest challenge to subsurface characterization at Forge, but I know you have some interest in using drilling vibrations, for example, for formation diagnostics. Do you want to comment on that a bit? And then I'll ask John the broad question of what the biggest challenge is to subsurface characterization.
Okay, yes. So there is an idea of using drilling vibration as an indication of a formation, mechanical properties, or sort of, implication of petrophysical parameters. So we also deployed high frequency drilling recorders for those wells, and we have observed high frequency torsional oscillations using those sensors as well. In particular, we in this particular event, we lowered our weight on bed, and then high frequency torsional oscillation was the severity was elevated. So this is kind of counterintuitive. We are looking into it. So this high frequency torsional oscillation is the actually, energy coming from interaction between the rock and the drill bit, and distraction of the shocks resonates to the lower part of the BHA. And we typically observe, frequency range between 50 hertz to up to 540, around 600 hertz. So it's quite higher than regular downhole drilling dynamics frequencies. But these are the indication of hard rocks, higher competency and brittle rocks. So using those high frequency vibrations, some people also characterize the subsurface makeup content of the rock. There are some companies using this technology and techniques. So that would be really interesting next step if John move this thing this technology to forward. But at the same time, we as the drilling dynamics point of view, we are drilling hard granite formation, and excitation at the bit is so high that probably the well that Fred is team of Fred and teams are drilling now have more HFTO traits. So I'm very much looking forward to see how much excitation is there, because this is this HFTO is very high magnitude and brings the accelerated fatigue to the lower part of the BHA, especially you're running something below the motor. So that's something once you started putting a lot of weight on bit, you're gonna excite more. I assume that you excite more HFTO, and we have to be careful about the damaging of lower part of BHA and the BHA components.
Thank you.
Yeah.
So John, I'll just ask you real quick, what's the biggest challenge to subsurface characterization?
High temperature, high impedance reservoir. People that drill subsalt can sympathize. Surface seismic, you can easily see the contact between the granitoid body and the alluvium above, but it's difficult to get much resolution. It's no different than in the oil patch. It's that tender area that's away from the wellbore, but at a subseismic scale that we're often really interested in, and imaging that and techniques to image that, particularly deep sonic interpretation from wellbore measurements are going to be really important.
Thanks. So got a question here, Fred, and it's almost, I feel almost like I'm setting you up, but how has machine learning been implemented to identify the limiters and optimize the levers available to the driller?
I would say it hasn't been involved at all, either in the machine learning looks at the past and predicts the future from the past. And the entire limiter redesign process is about identifying deterministically the exact thing that limits you from raising your weight on bit and doing something specific about it. So one is the stochastic approach and the other is deterministic. The stochastic approach is appropriate for manufacturing and some kinds of processes that don't require knowledge. But it only gives you some midpoint or some confidence level within that whole practice. It doesn't create a new practice, and that's the problem with machine learning. In some business environments, it's appropriate, but right now where we are, I liken it, people say, well, we can land an airplane, okay. Well, computers can land an airplane. Well, take a wing off and let's see how your computer does. That's drilling. We don't know the next fit. We don't know the dysfunction. We can't predict when stick slip's going to happen. We don't know boral stability. Boral stability has triggering effects on hole cleaning, pack-offs. We have too many non-repeatable, non-linear functions that talk to each other, the three deadly sins of machine control. And so it's a huge challenge to try to bring machine learning to the drilling operation. If you do, you might do a little better than a crew that you refuse to train. But you're not going to invent new practices, and you're not going to go faster than your midpoint of the past, because it's not going to make something new happen.
Thank you. So Tom, a quick question for you. You referred to Wear scars, is that what people commonly refer to as wear flats? And if not, what's the difference?
Yeah, just identical. Yeah, we're just talking about as that wear scar. Once you've rounded off that cutting edge and the wear scar across the diamond into the carbide, that's like we see that as a self-accelerated wear mechanism. It just gets worse, more weight's required, but it's too late by that time. So yeah, it's a wear scar.
So another quick question is we're getting down the end, so I'm trying to make them quick. What's the maximum weight on bit that's below the structural integrity of a 10 5/8" PDC bit that you're supplying to this project?
Well, that's a good question. We would rather look at I guess the weight and bit per cutter, but I know that Fred reached, I think, 75,000 pounds. So I was told. I think 66 was probably the average, but they spiked up at 75,000. So that's certainly much higher than we would normally apply on a 10 5/8. So that's getting up there.
Okay. Well, so you're avoiding the question.
Yeah, Doug, I tried to ask that question too.
I think it's going to be difficult for us. I think that's one of the challenges we have going forward is to know what is going to be the final limit, right? So what can we do to design? What can we do to maximize that depth of cut, reduce that wear life so that reduce that sliding distance to drill further and faster and faster. So, but do we know what that limit is at this point? It will depend on the bit design. It will depend on the number of cutters that are applying. It will depend on the number of diamondbacks that are applied to the design. There's a lot of, it will depend on the bit size and so many different variables. But so that's the best way I can answer that one.
This is, yeah.
So, Doug, I mean, Tom, I think it's fair to say that the hard rock geothermal drilling, we would like to have 85 or 95,000. So over time, continuing to press to redesign the limit, I think it's going to come back to the bit manufacturers to create literally design bits for very high axial loads and torques, and that'll probably have some effect on you guys.
And the motor manufacturers to build motors that will take that, and other jewelry manufacturers to have stuff that will fit in the drill string that'll do what you want to do. So we're going to have to go to the 1 minute closeouts. I can't remember the order I went in, but Tom, I'm going to go the other way, I think. And
yeah, great. Well, if you don't mind, I'd like to close out. There was a couple of points there were some good points being said by Fred and Junichi, and I just wanted to add, when we mentioned the bend angle going lower, that's definitely, I would say, a positive move because it actually puts less stress on the BHA and the bit itself. But in terms of reaming and avoiding that we have a tool, a dogleg reamer, that's able to take out those micro doglegs. And I think that having something like that in the drill string for future wells is going to help smooth out that hourglassing or that spiraling effect that we get in this hard rock. And so totally on board with what Fred said about, you get those pinch points with the stabilizers trying to pass through. It's going to be, right on size. So that was a point there. And the other point I wanted to make to Junichi, we need to get together because you mentioned high frequency torsional oscillations. We've just done a project looking into that. And also we've noted that even with the V-shaped cutters that I mentioned, when we look at the boreholes, we see a chatter from full round cutters. Yeah. And we've related that and see a very smooth, and it's basically that V form is actually stabilizing, a bit like the profile on a drill bit has a cone to stabilize it. You get the same stabilization, but cutter by cutter. And we're seeing firstly no chatter, but we're seeing a much smoother borehole. So yeah, let's get together and discuss that. Thanks, Doug.
Junichi, give us a minute.
Okay. Yes. So yeah, I briefly talked about high frequency torsional oscillations, but we haven't really understand how HFTO affects the wear and of the PDC drill bit. So that's something I mean, empirically, we drill many shale wells, and we haven't seen any correlation between bit wear and HFTO. HFTO always destroys something, some component in the drill string, just parting drill cutter or some other things. And talking about PDC cutters, this is very interesting because 1980s DOE supported this research and development and the commercialization of PDC drill bits. And I have seen a report from Sandia laboratory on the PDC cutters from 1990s. And because of a geothermal funding program from DOE in the 1980s, we had this remarkable evolution of PDC cutters. And like 1992, we had only 5 to 9% of the footage drilled with PDC cutters or PDC drill bits. Now, 2015, I've seen the number like 90% of footage drilled by a PDC drill bit. This is from Dan Scott from Baker Hughes. So it's really interesting, that we had a technology transfer from geothermal to the oil and gas industry. Now this technology is matured in a drilling oil and gas industry, and then back to a geothermal. And in the past few years, we have seen many improvements in PDC cutters, including wear resistance, all the shaped cutters, all sorts of shapes. So I'd like to really look forward to see more success on the latest and greatest PDC drill bit technologies.
Thank you. Thank you. Fred and John, I'm going to go with you, Fred, then John, and I'm being told that we're over time, so to keep our comments brief.
Tom mentioned interfacial severity. All the practices that we're developing, proving out, and there's several others that we can talk about that are important here. We'll publish those, and it's too late this fall. We'll get it in the SVU drilling conference in the spring. The practices, the physics, what can drill to decide, what can you engineer, and we'll also have a discussion of the workflow and how it may need to be adapted to the geothermal business model. And I think in geothermal, I would say the challenge is not technical, because you can get that. It's how you manage knowledge, and a big part of your challenge is the business model that you're having to function within is going to make that hard to do. And I think that's another longer discussion.
Thank you, Fred. John.
If I think about Forge, I think about 4 things. I think about connectivity, interconnecting 2 wellbores. I think about conductivity, interconnecting those wellbores with adequately conductive flow paths. I think of conformance, guaranteeing equal flow amongst the fractures. And I think of conversion, how much produce.
Thank you. And with that, we are going to close out this fascinating panel. I want to thank all the panelists in this discussion. I hope a lot of people learned something in this. I certainly have. I want to thank Jamie Beard and the Pivot team for putting this together, and I encourage everybody to listen to more of these sessions. It's been a great week so far. So thank you all, and we'll see you later.
Thank you. It's been great. Thank you.
Bye-bye.